I switch over to English, hope there is no problem.
Yes, sir.
কাৰণ এইবিলাক কথা এতিয়াও আমি শুদ্ধ অসমীয়াত ক'ব পৰা অৱস্থালৈ অহা নাই। ব্ৰহ্মাণ্ড অৰ্থাৎ the universe it came into existence after a big event, Big Bang, 13.8 billion years ago. This is an established fact in science. Now the question arises, not only one, several questions will arise that what is this universe, how big it is, and where is it start and where is its end. Then another thing is that we say that 13.8 billion years ago the universe came into existence. Is it possible to see that event or as close as possible? That means can we go back in the past at least 13 billion years? Is it possible? At least a few billion years back, if we are able to see how the universe was, that is a great thing for the scientists. Now, it was considered possible, and as Dr. Bhattacharyya mentioned, Albert Einstein had long back said that it is possible, and it is possible with the help of one particular entity that is called the electromagnetic radiation, light. So if we know how to exploit the properties of light, it may be possible to even go back in the past, because he dealt with time and space. So he thought that there is not much of difference between time and space. So what is light? Light is electromagnetic wave, moves at extremely fast rate, 300,000 kilometers per second, and in the known universe there is nothing faster than light. Einstein has already established that. But even this light takes some finite time to travel from one astronomical object to another in this vast universe. So we should also guess how big this universe could be. Some guess. Just one example is that the moon Earth distance is about 390,000 kilometers, and light takes about 1.3 seconds to travel this distance from the moon to the Earth. What it means in the other way is that when you look up at the sky at the moon, it is the moon 1.3 seconds old, not the instantaneous moon, but 1.3 second moon. The sun is about 150 million kilometers away from the Earth, and light takes 8 minutes 20 seconds to travel from the sun to the Earth. What do you see about the sun is that the sun is 8 minutes, more than 8 minutes old. So we are already looking at little bit of past. Now, how big is the universe? The distances are now we can call astronomical proportion. So the distance between the Earth and Sun is 150 billion kilometers. That is called the one astronomical unit measurement of distance in astronomy. But even this unit is not sufficient. So we go for another unit called 1 light year. That is the distance traveled by light in 1 year. It is 9.46 into 10 to the power 12 kilometers. You all know this. Now, how big is this universe? Take one example, our galaxy Milky Way. End-to-end diameter is 100,000 to 120,000 light years. Thickness at the center is 1,000 light years. And how many stars are there? About 400 billion. The sun is about 27,000 light years from its center. An interesting thing is that this galaxy was formed about 30 billion years ago very close to the edge of the universe. Since then, there are many more galaxies in the universe. Some are very old, some are newly forming. So how do we go about looking at these galaxies? Again, we have a problem, distance problem, how to measure the distance. So another unit is parsec, parallax arc second. Derivation is shown here. Finally, it comes to be 30.9 trillion kilometer, 1000 billion kilometers. That one's distance. That is the maximum unit we are able to have for meaningful measurement in astronomy. So with this now, we come to the main problem, how to look at the past of the universe. Now let us take some examples. The nearest star from the Sun, Proxima Centauri, is 4.246 light years away from Earth. What it means? What we see of this star today is how it was more than 4.246 years ago. Clear? Simple. Andromeda, another, the nearest galaxy from the Milky Way, is 2.5 million light years away. That means we see today what it was like 2.5 million years ago for Andromeda. Virgo cluster of galaxies, 65 million light years away. Now take it the other way. Suppose there are some intelligent creatures in Virgo galaxy. They are able to see, they are able to interpret, they can think like humans. And they look at the Earth. What you will be seeing is not today Earth, but what the Earth was 65 million years ago. And what was that?
Dinosaur to human.
There are no human beings, only dinosaurs on the Earth. So somebody in the universe, in Virgo galaxy, is still able to see the past of the Earth. So why not we should be able to see the past of the universe? Is it the question? Now, as per the theories of astrophysics, the first stars of the universe were found about 100 to 300 million years after the Big Bang event. That is about 13.5 billion years ago, and our Milky Way galaxy is considered to be one of that. The light from those stars have been traveling for 13.5 billion years continuously in space. When that light reaches our eyes, it amounts to seeing those stars 13.5 billion years ago, how they were. We should be able to see. Seems to be very simple, but it is not so simple because the problem is that during these 13.5 billion years, what kind of transformation the universe has gone through? Billions of years. And we know, thanks to Einstein, the universe has expanded in space and time both. It is not only space, but in time also. It's a little bit complicated. But he has given a very simple example how it is so. This is how it is thought that the universe has expanded. Okay. Anyway, you can see what it is. That the Big Bang has taken place, and from there the universe has been expanding. What we show here is only the space effect, but time effect cannot be shown here. It is only written how many billion years like that. And we are showing at the right extreme the modern galaxies, how they should appear. Now, this problem is solved by this illustration. Einstein has explained this. General relativity theory of Einstein. When the fabric of the universe expands from the instead of Big Bang, the wavelengths of any radiation present will also get stretched. like what happens in a swelling balloon. You can see from the left side to the right side, if there is a particular signal wave, how it has been expanded. Those who study about the signals, they know that the wavelength has increased, frequency has decreased. So that is the effect of the electromagnetic signal, which has expanded over 13 billion years. Another discovery by Edwin Howell Hubble is finding along with Lemaitre, the Hubble-Lemaitre law, that galaxies are moving away from the Earth at speeds proportional to their distance. This is what is happening in the expansion of the universe since Big Bang. H is the Hubble constant. Its unit magnitude is 73.4 km per second per MPC. MPC means mega per second. V is the velocity of the galaxy. Then what is the distance of that galaxy? We can find V by H in mega per second. And how to determine V? This can be determined from the another property of redshift of electromagnetic shift. These are all known information, known knowledge. And you know the redshift law. If the object is receding away from you, the frequency will decrease, wavelength will increase. If it is coming towards you, frequency will increase and wavelength will decrease. So this kind of redshift can be detected in the spectrum of the light received from the distant galaxies, whether it is approaching us or it is receding away from us. So we know the velocity of the particular galaxy. This is how in the pictorial depiction of redshift, that the incoming radiation, if it is the source is receding away, then the spectral lines will be shifting towards the radiant of the spectrum. And this shift is proportional to the velocity. Okay, this is just a pictorial representation of electromagnetic wave. Those who are not familiar with electromagnetic signals, it is for the benefit of them. We also know that this electromagnetic spectrum has high end and low end. High end is the gamma ray, X-ray, then as the frequency decreases, ultraviolet, visible light, infrared, then microwave, radio, like that, and afterwards it gets dissipated in the atmosphere. Another important thing is that any physical body at above absolute zero temperature, that is minus 273 degrees Celsius, till that time it will go on emitting infrared radiation. This is the property of all matter. Now, we consider that Big Bang has taken place at the right-hand side. The energy will be radiated in gamma ray spectrum, and as the universe expands slowly, as per Einstein, expansion is in space and time. Therefore, this radiation frequency will also get reduced, wavelength will stretch. So it will become X-ray, afterwards it will be ultraviolet, then visible spectrum, then infrared, then microwave, and radio wave, like that, it should go. And as long as the temperature is near above absolute zero, it will go on emitting infrared radiation. Now, soon after Big Bang, up to 380,000 years, that is considered the dark period. After that, the cosmic radiation started, and those radiations, because of the space-time expansion of the universe, today it is available as cosmic microwave background radiation, CMB. If you are able to detect it, then you can say that Big Bang is established. And it happened so. Part of this microwave radiation, they penetrate the atmosphere of the Earth. And even today, if you have a television set, without connecting to any particular transmitter system, You just put it on, and in the screen you will see some kind of hazy signal, and that is nothing but CMBR. And the scientists who were working for some other purpose, they discovered this, and they worked on it, they found what is the reason, and finally they got Nobel Prize. And it also inspired NASA and ISRO, NASA, National Aeronautics and Space Administration, ISRO, European Space Administration. They thought that more studies could be required on this CMBR, and they launched three spacecraft, Kumud, WMAP, and Plan, one after another, and they mapped the entire universe, that is the sky around the Earth, to map this microwave radiation and establish that yes, this cannot take place, and that this is the remnant of the energy that was dissipated at the time of Big Bang. Now, making use of Einstein's theory, general relativity theory, that was a problem. Einstein thought the universe is stationary. So we had to take, but actually here these equations were not getting balanced. So he had put one constant there, lambda, and somehow we managed to balance the left hand side and right hand side. But later on it was found that the universe is not stationary, and Einstein considered it as one of his biggest mistakes in his scientific career. But what happened? This Kobe, WMAP, and Planck, they confirmed that yes, the universe is not stationary, and from the data available, they were able to once again confirm Big Bang is taking place, CMBR is definitely there, and 13.8 billion years ago is the date with 4% accuracy that Big Bang has taken place. 13.8 billion years is the age of the universe. Now it so happened that some of the stars later on found that they are older than 13.8 billion years. So that they say is that their measurement error problem. Now, some parts of the universe, they are still able to emit in the visible and near infrared wavelength radiation. They are easily captured by our conventional photographic cameras. But more details of the early universe, they have to be monitored only in the infrared, because after this 13.5 billion years of traveling, all the electromagnetic waves, they are being forced to come to infrared spectrum. But some galaxies are still remaining in the visible range. So in the 90s, the Hubble Space Telescope, which operates mostly in the visible region and partly in infrared, that was put in orbit, and that provided very valuable information about the universe around us. But if we really want to know what has happened at the early part of the universe, the galaxies which are still trillions of kilometers away from Earth and billions of kilometers in size, emitting only the radiation is available today only in infrared. We have to have a massive size telescope, and that is what is James Webb Space Telescope, designed only for infrared wavelength. Now this is just the principle of optics. Magnification is the ratio of the two focal lengths. Then important thing is that resolution of a telescope. So these are expressions you will find in any textbook in physics, in optics. So Hubble Space Telescope 0.04 arcsecond in visible wavelength. James Webb Space Telescope 0.1 arcsecond in infrared wavelength. But still it is considered more powerful than Hubble. This is Hubble Space Telescope. Since 1990 it is in operation, going around the Earth as a orbiting telescope, and it is revealing many interesting features of the universe. This is the principle of normal optics only, since it is operating in the visible rays. Now, this is what is James Webb Space Telescope. It works only in infrared wavelength. It's meant for viewing the first of the universe. Now, compare Hubble and James Webb. It shows what is the range of the spectrum, electromagnetic spectrum. Hubble is able to cover, and how much James Webb is able to cover. It is mostly infrared, and it is going very, very close to the end of the beginning of the universe. That is a thing. This is how it is also shown that on the right side, if you see Big Bang event in that star, Hubble is stopping somewhere in between, but James Webb is able to come very close to the Big Bang event. Now compare these two. James Webb launched 2021, Hubble already 20 years ago. James Webb is expected 10 years lifetime in orbit. Hubble has already completed 30 years. Now important things are here that the mirror size of the James Webb is 6.5 meter, whereas mirror size in Hubble is only 2.4 meter. So this itself indicates that the resolution of James Webb will be much more than the Hubble. And weight-wise, Hubble is heavier, and James Webb is lighter, only 6,200 kg, because it has to be taken to a different destination than Hubble, and therefore the more they weight, the more will be the difficulty in carrying it to that point in space. Compare the reflectors. The mirror which is used by Hubble and the mirror